那个省事情。下周又要考试，这讲下周考试的下周看来还考试，16号、15号有考试，3个考试。除了这个75都要。第二个题。咱们可以出去学几号？15号。你休息直接就约到10。
就是你有下，你15号下完了。
啊，
就是刚刚那个。
啊。
就是约15号。
我就随便你说，我不能进约15号。
这才4个。
周5吧。这不是点，这是什么 ？Smart 去那个站起来考试。对，这里在这说他这里写了，你要是用他的车25刀。
不用。
不用他的车70刀。不是，用他的车额外加90付。就是我他可以。如果要自己车的话，你要必须把保险带上。
Homework is due before you vote. You voting tomorrow? You're voting tomorrow? Why?
Are you voting tomorrow?
I'm not vote. I had a friend one time that he said he doesn't vote because he claims there's no difference between Democrats and Republicans. But there is a difference. One starts with an R and the other starts with a D. They are what you call politicians. How's the homework? Easy?
No.
Hard?
Yes.
Why is it hard? Is the homework hard? Which one you having problem with? Okay, number one says something about it says something like a random variable. I'm going to use A or B. A random variable X is equal to A if another random variable zeta is equal to 0. Right? And a random variable X is equal to B if the random variable zeta is 1. Okay, we have A is sine pi t and B is t. Two numbers, right? They just have the t in. And so the probability that the random variable X is equal to A is equal to the probability that the random variable zeta equal to 0. And in this particular problem, the probability that the random variable was 0 is equal to what? 2/3? 2/3. And the probability that the random variable is equal B is the same as the probability that the random variable zeta is 1, and that's 1/3. And so that means that fx of x is equal to 2/3 fx is equal to the probability that the random variable x is less than or equal to x, isn't it? So if the random variable is less than A, this is it's 0, isn't it? X less than A, or less. It's equal to 2/3 if A less than X less than B. And it's equal to 1 if X is greater than B. And so what we have here is 2/3 u of x minus A plus 1/3 u of x minus B. And so f of x so here's A and here's B, and 2/3, 1/3. That's it, right? So you just plug in what A is. A is sine pi x. So you get different values, whatever you choose for t. And it looks like if A is the sine of pi t and B is t, then at t equals 0, a equals b, right? It'd be 0. So that means that the function goes up to 1 at 0. Goes up to 1, t equals 0. So last time, it looks like we'll never finish this Bernoulli telegraph, right? Telegraph. Okay, so I have here now autocorrelation. And so we have this telegraph signal. So it changes polarity. Polarity change at a success. Polarity change at each success. By the way, if you look at this, it starts at 1. Right, starts at 1. It could start at 0. Could start at 0. So now, autocorrelation. Rx at T1, T2 is the expected value of X at T1, X at T2. It's equal to that, which is, it looks like a double sum. Double sum. So I'll just write it as an integral, x1, x2, f x1, x2, x1, x2, dx1, dx2. Really a sum, not an integral. Actually a double sum. So we're just using the two integral signs to mean double sum because it's a discrete process. Okay, so that is x1. x1 can take on values here's T1 and T2. So the function x of t can take on values +1 or -1. So it can take on +1 and take on -1. And x2 can take on values +1 and -1 and +1 and -1. So we multiply those two, right? See, those two multiply. multiply. This one is the probability that x1 is 1, x2 is 1. This one, see, 1, 1, 1. 1 minus 1. So the probability that x1 is 1, comma, and x2 is minus 1. This one is the probability. This is plus, plus, plus. Probability that x1 is minus 1 and put in a bracket, and x2 is plus 1. And this one is the probability that x1 is minus 1. I did it, put a comma. And x2 equals minus 1. So I'm integrating, calculating the expected value of the product. So we need the joint densities here. Need joint density. But we don't have the joint density. We have the probability that x1 equals 1 and x2 equals 1 equals what? Probability that x1 is 1 given x, that's x2, given x1 is 1 times what? Bayes' theorem. Probability that x1 is 1. This one is the probability that x1 is 1, x2 is 1. That's the probability of even, isn't it? Even number of events between T1 and T2. Of even number of successes, right? Not events, successes. And what is that? That is 1/2 times 1 minus 2p raised to the power n. There are n events between T1 and T2. This is the number of successes between T1 and T2. Even this is the number. This is the number of even successes between. That means the polarity changes, right? So this is 1, and that's 1, means 2 polarity changes. 2 events. This between here and here. An even number of events. 0. 0 is an even number. between here and here, we got 1, 2, 3, 4. Isn't that something? And so that number is 1/2 times 1 minus 2p, because we did the algebra. The probability that x equals 1 and x2 equals 1. The probability that x1 is 1, let's just say x1 occurs at t. Let's say x1 occurs at t equals 1, right? That's the starting point. Right. So at the starting point, it can either be positive or it can be negative, right? But if we flip a coin, and if it comes up heads, we're going to say it starts at plus. If it comes up tails, we're going to say it starts at minus. But nevertheless, no matter where you are on that curve, the probability that whether x1, whether t1 is 1,000 or 10,000, the probability that it could be +1 or -1 is still 1/2. And so this number is 1/2. And so that is 1/2 times 1 minus 2p raised to the power n times 1/2. The probability that x1 is 1 and x2 is -1 is the probability that x2 is -1 given x1 is 1 times the probability that x1 is equal 1. And again, that's 1/2. This amounts to an odd number of events, right? If it changes this thing changes polarities an odd number of times, right? If you're here and here, or if you're here and here, or if you're here and here, right? If you're here, odd number of times, even number of times, here and here. If you are here and here, still an even number of times. If you are here and here, it's an odd number of times. If you're here and here, it's still an odd number of times. So probability x1 equals -1 and x2 is 1. And the probability that x1 equals -1 and x2 equals -1. This is probability that x2 is 1 given x1 is 1. I guess we've already done that, haven't we? So 1, 2, 3. Okay, x1 is -1. probability x2 equals minus 1 given x1 equals minus 1. It's still 1/2 over here. Let's see, this is minus 1 plus 1. So 1 given minus 1. There. So polarity change from here to here, or from here to here. This is 1/2. This one here is 1/2 times 1 minus 2p raised to the power n. Right, this one should be plus. So you have 2 of these and 2 of these. So we'll write the answer. Rx T1 T2 By the way, what does this number come out as? It's positive, isn't it? It's a plus 1 times a plus 1. This one is a minus 1 times a minus 1. This is plus times minus, it's minus times plus. So you have 2 of those, 2 each. So you have 2 of the plus 1s, 2. Then you have 1/2. Then you have 1/2 times 1 plus 1 minus 2p raised to the power n. Plus, you got a minus 1. Now you got 2 of those. The probabilities. Then 1/2 times 1 minus 2p to the n. Well, if you do the algebra, comes up 1 minus 2p raised to the power n. 1 minus 2p raised to the n is number of events between T1 and T2. Here we had T2 greater than, I think that's all. So T2 was greater than T1. And if T2 greater than T1 and it is equal to 1 minus 2p, T1 minus T2, T2 less than T1. So I write equals 1 minus 2p, T2 minus T1, T2 minus T1. By the way, this number, you want P getting very small. So this number might turn out to be a problem. But in any event, this thing should go down like that. The Bernoulli. The Bernoulli. Well, that's a simple process, isn't it? Bernoulli. And its cousin is Poisson. Poisson process. Okay. Here is T1 and T2. The probability, let n a T1, T2 is the counter. Count successes between T2 and T1. So the probability that counting the successes between T1 and T2 equal to K. The probability that are K successes between T1 and T2 is e to the minus lambda T2 minus T1 times lambda T2 minus T1 raised to the power K over K factorial. By the way, the textbook doesn't even do what we just did on Bernoulli. You know why I think so? It's because it's too simple. The textbook doesn't do things that are simple. The number between T1 equals 0 and T2 equals T. N of T equals to K. It's e to the minus lambda T, lambda T raised to the power K divided by K factorial. So this is still the same Bernoulli problem where we're counting successes, but the Poisson process basically has that probability Bernoulli Bernoulli versus Poisson. Bernoulli has the probability of a success is P. Of one event, the probability of a success is P. If I do n experiments, what would be the average number of successes? I did n experiments. I did 100 experiments. What is the average number of successes? I have $1. Answer, going for $1. We need an auctioneer. Answer, going for $1. Anyone for $1? Going for $1. Going for $2. I do 100 experiments, and the probability, I throw a die 100 times. And if a 1 shows on the die up, I call that a success. What is P? 1/6. And if I throw the die 6 times, what is the average success? 1. If I throw the die 60 times, what is this average success? 10. So the average is n times P. Average number of successes out of n experiments. That doesn't mean I get NP every time, does it? I can take this. We might as well go to the lab. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is, there's 1, 2. So the average number of success is 2/10. So it's P times N. So Poisson says, I'm going to let N get very big. And Poisson says, I'm going to let P get very small. And Poisson says, you know what? P times N equals lambda. Oh, Poisson, he thought that 0 times infinity was lambda. Zero times infinity can be anything, can it? Okay, well, in this case, P times N is lambda. So one goes to infinity maybe a little slower than the other goes to zero. But what we did on the Bernoulli process, we said, oh, how many successes out of n, right? So I could count the number of successes. Or I could do the expected value. The expected value, k. Well, I can do here the number of successes here, and this, so here's the k now. The number of successes in that interval. So over a long period of time, you just take, kind of the average. So the Poisson and Bernoulli are very similar. The expected value of n is equal to e to the minus, it is the summation k equal to 0 of k times the probability n equals k. And so this is summation k equals 0. In Bernoulli, n is going to infinity. So k equals 0 to infinity. K times e to the minus lambda t raised to the power k over k factorial. Oh, this thing here can come out. Can't take out anything else. And then k here kind of lets us sum from k equals 1 to infinity. And this is lambda t raised to the power k. No, lambda t raised to the power 1 times lambda t raised to the power k minus 1. And this is k minus 1 factorial. Oh, so that means we take that outside. Lambda times t. There's no k there. So k minus 1 equals to L. And so the expected value of n is equal to lambda t e to the minus lambda t. And so if I do this transformation, L equals 0 to infinity. Lambda t raised to the power L over L factorial. So dot. You know what this sums to? I got $5. got $100. I got $1,000. Now we're playing with real money. Did you know that e to the x is a summation n equals 0 to infinity x to the n over n factorial? Did you know that? Sometimes this thing gets stuck. I'm gonna take a nap while this. Oh, it says no internet. Not again. Firefox, are you there?
No internet connecting.
Why does this not want to connect?
I don't know, we're gonna have to get in contact with OIT, but sometimes restarting the computer helps. Now we need to check down here to make sure the cable's connected.
You know what? Wireless seems to work better than Ethernet. Maybe. Oh, that looks like it's up. Nope.
I have to try restarting.
Oh, you restarted?
I haven't restarted yet. I made sure the cables were connected.
It's gonna ask me to sign on.
Right.
What did you do? Just restart it?
I did just restart and confirm that the cable is connected correctly.
You know, we've had problem with this one. The one next door, there's not a issue.
The same thing.
No, just this room. Maybe there's a ghost in here.
Right.
See, look, it doesn't. Where is the machine? Is that it?
Yeah, this is it right here.
Maybe we should switch to Dale.
Yeah, you can call OIT. Hi, I'm in room 184 in Carruth, and we're having problems connecting the PC to the internet. Yeah, we're trying to restart it right now, but it's acting weird. It's taking a long time. Yeah, it's 46771656. Okay, thank you.
Who'd you call, Merlin?
IT. They're gonna send somebody down to fix it.
Wonder if this'll work. So here we go with oh, we just hit that button right there, right? So X to the n divided by n factorial I'm going to sum from sum on n from 0 to infinity. Let's see. F F fx underscore comma n underscore underscore colon equals what did we have for Poisson? Exp minus lambda. You know how to write lambda? Escape. L lambda space T. K and then we got lambda times T. Bracket lambda escape lambda times T. I'm going to raise that to the power n. So I hit Control caret. I get n. And I'm going to divide this by k factorial, or xn. Okay, I'm going to put over here k underscore, comma. And I'm going to take this, Control slash, and put k factorial. Right, so now we have a function that we've defined. So I hit Control return. Suppose I want to find the expected value of k. The expected value of k. I'll write EK. Just between you and me, that means the expected value of k. That is equal to, we're going to sum that. K times F. I might as well put lambda T in there. Lambda T. That's going to be x. Okay, so I messed up here. X. X. So I'm going to find this summation.
Having access problems with the internet. On which computer?
This thing has been intermittently bad. Look, there isn't having trouble there. Okay, so F lambda T comma K Okay, so I got another problem up here. That should be K. And we can take out the So sum k f lambda t k takes care of that. I'm going to sum this on k from 0 to infinity. Bracket close. Okay, you ready? Cross your finger. What do you think of that magic? Expected value of kk equals, I'm going to just take that sum and copy it. And I'm going to put k times k minus 1. Look at that. What is the expected value of k squared? This was the expected value of k times k minus 1. So I want to find the expected value of k squared. That's equal to copy,
Oh, can I get at the keyboard?
Control V, Control caret, squared. Would you like to use Mathematica on tests? So the reason we're doing that the number of successes we're interested in the expected value T1 times the number of successes in T2 minus T1. You know why we're doing that? Why we're worried about the number of successes from 0 to T1 and the number of successes between T1 to T2. Why are we doing that? Because they're independent, aren't they? Remember we talked about that. So here's T1. Here's T2. Right. So you have events here. By the way, when we were throwing the dice, we throw the dice here, but you only get successes every so frequent. Point like that. See, those are successes. And these down here are events. So we throw the die here.
The issue is.
What was that? Is there a ghost?
I'm sorry, that was my walkie. I forgot to turn it down.
So we throw the dice at the X points. And when a 1 comes up, here's a 1. Right? So we throw 100 X's and no, 60, we have 60 X's, but we only have 10 successes. That's on average, right? So, the number of events between here and here, and the number of events in T1, in T2, the number of events between here and here depend on the number of events. You know, we've said that about 100 different times, right? And so the trick to evaluating this is the expected value in T1, in T2, right, minus the expected value of n T1 squared, right? So it looks like I calculated that. K times K minus 1, that was T squared lambda squared. T lambda squared, T squared lambda squared. Right. This was T squared lambda squared. And this one was something else. Oh, that was T times lambda plus T squared times lambda squared. Lambda T squared plus lambda T squared. So we are back then to calculating probabilities. The expected value of n times, oh, it looks like I put n minus 1. That's equal to lambda t squared. And the expected value of n squared, lambda t squared, lambda t. I think we are going to work next time on the telegraph signal. Using Poisson. Okay. Homework. So you get 10 minutes. Hey, look, it came up.
Yeah, what happened was it was installing updates, and so that's what's caused it to hang out there.
Okay, that's it.
Can you explain the question too?
So it's updated?
Yeah.
Here, I'll get out of your way. I've had trouble with this machine that I didn't have with other machines around.
So were those your papers that I hid?
Okay. Yeah. Looks right. Looks okay. That's it. Class over.
I'm sorry if they took the inopportune time to update.